Okay, there we go. So I'll now request Professor Chandrasekhar Yeramalli to start his webinar. So you can share your screen and you can start. Yeah, but you are still on mute.
Sorry.
Yeah.
Okay. Thank you, Professor Pant and NACDeC organizing team for this opportunity to do this webinar. Okay. First of all, let me share my screen. Then where is the screen share button? Yes. I think you can all see my screen now.
Yes, screen is visible.
So first, let me just say that this webinar is not going to be about some particular design. So there are two things that maybe I want to clarify right at the beginning. See, there is a design and there is the design. Now, what is the difference? The difference is, as an engineer, as a structural engineer, I can always design anything I want. I can design an aircraft also. All of you, with your basic structural engineering knowledge, given some information, and this, you can design anything you want. But that may not necessarily get certified and be allowed to fly or operate anywhere in the real world by the authorities. The one that will be allowed to do that is basically the design, because that design is going to satisfy all the certification requirements, standards as prescribed by some professional bodies or government agencies. So there are two aspects to design. So one is the general design approach. Basically, given a problem statement, how do I go about designing something? After we do this, the second problem now comes up is, can we get this design certified by the required agencies or authorities or whoever? That is a separate problem. What we will tackle here in this webinar is, or rather my objective or my interest or my intent is to just talk about a general design approach. Given a problem statement, given that you have to design some vehicle or something, how do we go about designing the structure? Okay, so I just want to make sure all of you are clear about that. This is so that you understand any problem, all of us can design. There is nothing big deal about it. So the second question of, as I said, that is where the issues are, but that is more of an issue of getting it certified and to rate it to a certain requirements. But design itself is always having a few fundamental steps, and as long as we go through all those steps, I think all of us can become designers. Okay, and my interest is to share with you those few things, and so that all of you can go about designing your particular vehicle in this competition in the way in which you have envisaged the structure and the geometry and all that. But at least you should be aware what are the basic things that you should check for in a general design. So that's why I put this title as a general design approach. So this is again just a very overall overview of how a typical design problem evolves. This is related to aerodynamic aspect, like a turbine blade, but it can be applied to anything. So in a turbine blade, for example, the important thing is to get the geometry right. And the geometry means the airfoil geometry is right. And once that is, let me open the pen. So this is what I'm showing here, the blade airfoil sections. So a turbine is made up of a series of airfoils which are arranged along in the radial direction. And so that is the job of typically the aerodynamics people or aerodynamics engineers. They would decide which airfoil should go at what section and all that, and what type of airfoil, what should be the orientation, like the angle of attack at which it should be placed. And all these things will be decided based on aerodynamic calculations. Once that is done, what we get is really a surface model, a geometry of the turbine or a propeller or whatever. Now you take that, and that comes to the, say, structures group, because that is only a surface. We have to make that into a reality. That is where the structures group has to now, okay, given a particular geometric profile, what kind of material and other requirements, for example, the operating environment, the temperature and all those things, what kind of material should be used, and also cost is another big important. So those things will be decided, and we create suitable sections of those which will fit into that surface, so that the outer surface remains unperturbed, whereas internally we reinforce the surface. And once we do that, we go about doing some structural analysis. We have to do we apply the loads, we look for deflections and all that. And then this is a composite, for example, then you decide the layup and all that. And there is optimization basically done here. You iterate. Usually, unless it becomes really terrible, the aerodynamics is not tampered with that much. But there are many times when in this iteration process, it may be, required that the aerodynamics group has to rethink the surface geometry and come up with maybe a different geometry. Sometimes the aerodynamic surfaces may become infeasible in the structural design, so they might have to compromise. So this kind of iteration is done, and once this is done and we reach a satisfactory result in terms of some design criteria that were decided a priori by the design team, then based on that we decide, okay, this is the final design. There will be a review and all that. But once that is done, that goes to the manufacturing team as a drawing. All of you must have learned engineering drawing. So that is where that engineering drawing skill comes into play. You have to create design drawings, and actually design drawings, which should be in case of, say, composite materials and all, it also, there is a separate manufacturing drawing has to be done. And these manufacturing drawings will go to the shop floor where the part will be manufactured. And in case the part manufacturing, again, it could happen. Suppose if the designer has no knowledge of the manufacturing capabilities, he might design something that the manufacturing team cannot make it. Then again, it will come back to square one. We have to redo the design, but it doesn't happen often or rarely, because most of the time there is a close integration, but it is required. It is not something that happens by default. That integration has to be done by deliberate manner by the design team, so that the manufacturing team is also incorporated into the design loop, so that they are aware about what's going to happen and their inputs are also going into the design. So once this is done, then the part is made and it goes into the field as a product. So this is a really high level loop of design and manufacturing thing. Now, coming to your particular problem, this air ambulance problem that has been given, we can see that it has got this kind of emission profile and some of the specs on the mass of patient, paramedic, the kind of range, cruise speed, cabin volume, and all these are given. I just took this from the design, the document, the problem statement from the website. So this is the problem that all of you are looking at. Now, I'm assuming all of you have already done quite a bit of work on this and come up with some configurations and all that. Now, the key part is how do you get to make it? There are two approaches to make this. One is do empirically, make some part, try it out. If it doesn't break, it's okay. So we use it. But that kind of design technically is not a design as such, because it's an empirical thing. It will be as good as, until it's first failure. Because every time you make it fly, you don't know whether you are breaking the envelope of its design. Because there is no design envelope as such originally thought by the designer, because it's an empirical thing. Many times, actually, when people don't know the formal analysis techniques and how to go about approaching the design, people tend to do it in this gut feeling fashion. We make something, we try it out. If it fails, we reinforce that particular failed part, and we keep on doing like that. And somehow the last one that works, we stick to it. And nothing wrong in that, but it's just that it is not really a technical design. It's just as if somebody who doesn't know any basic engineering has done that work. As long as it flies, I guess it's okay. But we'll try to see if we can do it in a better way. So I'm assuming all of you are mechanical or civil or aerospace engineers. So all of you have done basic strength of materials and basic mechanics of materials and some solid mechanics and these or FEM or these courses. And all of you are familiar with CAD modeling and all that. I'm assuming that. So first thing is, what is the difference between analysis and design? I don't know whether webinar, I don't think it will be a two-way, I'm assuming, Professor Pant. So maybe I'll only answer the question.
No, it's not two-way. In the end, we will open up for questions.
Yeah. Okay. So what is the difference between analysis and design? Most of you have done a lot of analysis courses, strength of materials, finite element analysis, the course itself, finite element methods. All these are basically where and we have to solve it. So cantilever beam problem, the problem is given to us. There is a cantilever beam of so much length, so much dimensions, material properties are given, the load is given, the load application point is given, and then we are asked, what is the deflection in this beam? And we go about solving it. Now, design is different. Design is, can you design a cantilever beam which can take so much load at this location, and its deflection should not be more than so much, X magnitude, mm, or whatever. Nobody has given you anything else. This is an English language problem that has been given to us. So now, as an engineer, we basically have a white paper and only whatever we know, and we have to now come up with a cantilever beam that will satisfy the requirements as posed by the end user. Okay, so that is a design. So design basically is the problem where we create something which will satisfy the requirements of the end user. So that is why design is slightly, it is not difficult, but it is uncomfortable for many people, because we are used to studying in a system where everything is provided to us and we solve the problem, because all the information is given to us and then we apply a formula or we apply some other thing and we solve it. Whereas design, nothing is given to us except the end requirement that the user wants. Now it is our job to go and pick everything. We have to decide, okay, what should be the material that will be there? We have to decide the geometry of the beam. We have to decide, in case of a cantilever beam problem, I'm saying, we have to decide the geometry, we have to decide the material system, and we have to decide, how much safety factors we want to use. So all this kind of information we have to create ourselves. Okay. So we have to create ourselves. And what this does is, so there is a certain fuzziness or rather discomfort for a typical engineering student, because we have not been trained to do this way. We are always given problems and we solve them and we are happy. So now when you come to a design, that is not the case. As I said, you have to create your own problem. So first thing we have to know is, how is this design driven by? I mean, what do I mean by driven? What I mean is, like, whenever we do some activity, there will be some objective which will drive us. Either we are limited. Suppose I want to go, I have a car and I'm driving I want to go very quickly from point A to point B. one thing could be I could be limited by the power of my car and I cannot go faster than X speed. Or the other thing could be that I have a very good car, powerful car, everything, but I'm driving in front of IIT Powai, where nothing can move better than a bullock cart speed in peak time. So how does it matter then what kind of car you have? So you are limited by some other constraint. So then my driver becomes the traffic on the road. If the road is empty, then my driver becomes the shortest time problem driver becomes the power of the car. So in the same way, when I'm designing a cantilever beam, for example, there are two things that typically drive any design. One is the deflection. So if this is a cantilever beam and I put a load P, and let's assume I have taken a material of modulus E and moment of inertia I, my deflection at the tip is PL cubed by 3EI. So what happens is when I apply this load, the beam will deflect here. At the tip, it will be the maximum. Now, what are the things that are driving this problem is, suppose now I say that my cantilever beam has to be maximum allowable deflection is, for example, I'll draw it slightly lower than what has happened. So this I'll say is delta allow. Now, if delta is greater than delta allow, my cantilever design problem for the first iteration, okay, this is again iteration based. So I have assumed something, because in the design problem, as I said, nothing is given to us. I'm going to assume a material system. I'm going to take an I value and I'll apply the load and I'll do the deflection and I get a delta which is greater than the allowable deflection. Then I am limited by my delta. So now I'll do one more iteration where I will change either E or I or both. I can do anything. See, as a designer, we have absolute freedom. So I'll change one of these or both. And then I'll see that delta is less or equal to delta allow. So that I am within the allowable deflection. So now what happens? That means I am, if I think about my constraint space as two pipes, say if delta is this lower one, then I am sitting here. My design is sitting here. That means I have designed my cantilever beam in such a way that the deflection that the beam will undergo under the design loads or the applied loads is exactly equal to the allowable deflection or slightly less than that, which is good, okay? Because that means I have utilized the maximum allowable deflection for me so that I can design my beam with the smallest I, okay, possible, so that I get to the delta allowable and I'm happy. That is one way to design. Now, another limit that typically happens in design is stress or strength. So the deflection or stiffness based designs typically happen with weak materials. So if I have, for example, modulus of elasticity of glass fiber reinforced composite, GFRP, it is about 40 GPa. Now, suppose I come up with another material, which is, say, E-carbon. So this is CFRP. Sometimes this digital pen scratches, so sorry. So that is about 120 GPa. Now, when this 120 GPa material is put into this, imagine in this same beam equation, PL cubed by 3EI, if I put 120 GPa, between 40 to 120 GPa, how much difference? There is a 3 times difference. So that means my deflection, if I keep everything else same, my deflection would reduce by 1/3. Okay. So now what happens? Deflection has reduced by 1/3 means I can reduce my I also little bit more than what it was for a glass fiber composite. And by the way, what is I? I is the moment of inertia. I mean, I didn't clarify this, assuming you are all familiar, but just saying I is moment of inertia, which is again a function of the thickness of the profile. So moment of inertia of a rectangular is rectangular beam is BH cubed by 12. So where H is this and B is the width. So now what will happen? I can, because E is now higher for carbon, I can actually increase my E. Okay. Sorry, E has increased, therefore I can reduce my I, so that I reach the delta allowable. But in that process, since I'm reducing my I, and that means if I reduce I, somewhere my cross section is changing. You know, it's BH cubed by 12, no? So I'll have to reduce, say I make my rectangle smaller. But now if I make my rectangle smaller, stress is proportional to area, cross-sectional area. So it will happen that at some point, I reach sigma to be greater, or, you know, I could be greater or equal to the sigma allowable. So in that case, then what happens in this particular design, I might reach a situation where I'm not too worried about deflection. I have a lot of margin in deflection because my material is very stiff. I will have enough margin in deflection. My delta is, in this case, delta is very much less than delta allowable, but sigma will be just greater or equal to sigma allowable. This is the kind of design I'll get with stiff materials like carbon composite. In case of glass composite or weaker materials, or, you know, materials with lower Young's modulus, I will be delta is, you know, greater or less or equal to just delta allowable, and sigma will typically be having a lot of margin. Sigma is very much less than sigma allowable. You know, in fact, here also we will always design to less or equal to sigma allowable, assuming it's close to that. So these are the two difference. So whatever choice you make in your airframe, like if you are using carbon composites or glass composites, you will see this happening. It is not a big, you know, you always want to make sure that in your design, one of them is approximately equal or close to sigma allowable, less or equal to, okay? Similarly, if you are going for deflection limited design, then your delta has to, you make sure that the maximum deflection is really close, or, you know, less than, it should be less than, but it should be close to the delta allowable. Similarly, sigma, then you don't worry about sigma. In case of a strength limited design, your stress, maximum stress in any of the members has to be less or nearly equal to the sigma allowable. Because if you keep too much margin between sigma allowables and delta allowables, you are basically wasting material. That is the only thing. There is nothing wrong. You can keep both of them to be very far away from their allowables, but it's just that your design will become bulky because we are then using more material than that is required by the design. Okay, so this are the two key things that you have to keep in mind when you're going for designing of any structure. And in your case also, I think this is what you should first thing you should check is this. Okay, what is your limiting thing? What is it driving it? The thing that is limiting is basically becomes your driver, because that is what will force you to change the design. Okay, then the next part is, I sort of went ahead and told this, but I wanted this point to be clear: deflection and stress limits. But the most important part in any structure is the loads, because ultimately the whole structure is being designed so that it can resist the loads that are being applied. Now, load itself is a huge, it's not a simple thing. It's not like your problems where somebody tells you P equal to 100 Newton, you apply it. Because in reality, getting loads itself is a huge process. Now, in case of a aircraft design or these kind of designs, you will have a Venn diagram from which you can get the load factors, and from there you can apply loads. You also have, basically loads in these kind of things are in various conditions like takeoff, cruise, accelerated flight, extreme gust, unsymmetric loading. Say you have a quadcopter, two propellers stop working, or sorry, one propeller stops working, and or three propellers stop working. Suddenly there is a, what kind of imbalance is going to happen there? Or say you suddenly you are just accelerating, say only two of the propellers, and unsymmetrically there will be some type of a imbalance, so movements which will be generated. All those things, you may not have to do all these things in this particular design competition, but I'm just saying that these are all the different types of scenarios in which loads can be generated. So, and also then the loads due to cargo, whatever you're carrying, the dead weight of the structure, which basically is the weight, self-weight of the thing, fuel, or in case of this, batteries, all these things also will become loads for the particular frame. Okay. Then there could be other loads also. If, for example, I mean, in this case, it may not be required, but you might have to account for electrical, lightning strike type of situations where, how does that, it's not a load in the conventional sense, but it has to be taken care of by the structure. The structure should be able to withstand the strike. So there could be other things. Okay. So then the other thing is that, see, we are always used to thinking about loads as this load is acting, that load is acting, but in reality, many of these loads will act independently or in unison also. They could be coming in a combined case. Then that will lead to different load cases. So again, one has to think about these load cases. Many situations, since many of these are designed, if you do Google search or do some reading, you will find there are already some load cases which have been defined. If not, also, you can just think on your own and say, okay, what combinations can lead to a disastrous situation where the loads will be more than when they act independently. And one could look for those cases. Okay, and you can define for yourself and do it, because ultimately somebody has done this job before us. Therefore, we might find a report somewhere. But if nothing is there, then it is our job as a designer to think about those situations where multiple loads can act together and create a detrimental situation. So it's so that has to be done. As a designer, that is our job. Now, the other situation is repetitive loads. I mean, this whole your takeoff, cruise, land, again takeoff, cruise, land, you can think about it as a one load cycle. Now, this load cycle, if repeated over multiple times, can lead to something called as fatigue loads. Basically, there's a cyclic loads. So the stress itself may not be much high. I mean, it is nothing near the breaking stress of a material or failure stress of a material. But when even a small stress, if repeated over a long time, material can fail, and that is called as fatigue failure. So this also has to be accounted for in design typically. Now, so these are all the different loads that one should account for in the design process. Okay. Then the second part that has to be looked into is the materials aspect. See, material is another most important thing. If you think about design as a triangle of say, what is the functionality that you're looking for, then the other two would be like the loads that are going to act, and then the third is the materials with which this particular function will be achieved, material and geometry. So material selection is again driven by the function. What kind of function are we looking for? What is the functionality of the product and what is the end user requirement and all that. Then the other issue is, we think about some material, but suppose we don't have the manufacturing skill or we don't have access to that material. Maybe we cannot purchase that material. We may not be able to, get it in time, whatever, some access to resources could be an issue. Then the third issue that drives material selection is cost. Materials are usually the most costly part of the whole structure because that is what makes the structure. And so if you want to get a specific material, then they might be expensive. And so cost is also a driver. So choice and access to right material system is key to a successful design. Many times it is the bottleneck in the design. For example, nowadays modern aircraft fighters are made with carbon composites, but we don't make carbon fibers in our country. So we need to import. If somebody doesn't sell us the carbon fiber, our design process will be stuck. So in the same way, there are ceramics, some specialty ceramics, which we don't have access or we cannot make it, for example. Then we have to get it then again. So what happens then? All your paper design will be put to a full stop if that right material system is not available to us. So in the same way, when you are choosing materials for your competition, for this design competition, first make sure that those materials are available to you, accessible to you, and you can get it. Because once you do all the design calculations, assuming a certain material system, and at the end, suppose you don't have access or it is too expensive for you or whatever the reason, then you will have to redo the whole thing, because the material change happens means everything has changed. So make sure that you make the right selection of materials. And before you do that, you check for all the availability, accessibility, manufacturability, also functional requirement point of view, whether this material system will satisfy cost, etc. Okay. So that is the second aspect, which is very important to the design. Then the third aspect is the analysis and design tool. So I'm assuming all of you will have access to, CAD modeling software, finite element analysis software. And the most important thing, that all of you are technically proficient engineers with an understanding of the basics of engineering, because all these softwares will be of no use if you cannot figure out what to do and how to do. So, and basic things you should always be checking yourself. Whatever software we use, it is only going to give us what we have input to the system. If our inputs are wrong, if, say units mismatch, material systems, typically when you look online, you will find material properties given in various units. Loads you will get in some other units. And if you are not doing the conversion properly, you are solving a problem which is of nobody's problem. Okay. So make sure that, these kind of things are not, because there is actually, in reality, it happened. Lockheed Martin sent a probe. It was a NASA Lockheed Martin venture, I think. They sent a probe to Mars or some other outer, one of those outer belt, actually not Mars, maybe some other thing. And the probe, I think, crashed into that planet or moon or whichever one they sent. And later on, during a, basically post-mortem analysis of the whole operation, the failure, they realized that there was a unit mismatch. NASA worked in SI system and Lockheed Martin worked in the old FPS system. And somewhere they made a mistake and they didn't convert. So make sure that in your design, you are not doing any mistake like that. Get your units right, create a standard unit, requirement among all your team members. Make sure that whatever goes in a design document follows the same SI unit system. I'm assuming NACDeC will accept only SI unit, because that is the standard which in India we operate for all design. So you should only use SI units, and make sure that whatever data you get from outside, when you put it in the report, make sure that it is converted to SI system. Don't just, because this information is available there, don't dump it into the report, because that will go into your design calculation by mistake also. It is possible. And then the whole thing will be wrong. So check for all these things. And again, as I said, design always starts from scratch. So initial design, you have to start with a guess, and that will be finalized over many iterations. So what is the steps I would say is, one is identify your design objectives. Second, choose the right material system. Identify the loads and estimate the loads. Perform simulations with some geometry, whatever guess you have, and materials, and apply the loads. Then safety factors is actually another important thing. Maybe I think I missed that part in the slide. So what you do is, see, safety factor is required on both material properties as well as on the loads. So let's talk about material properties. For example, if there is a, you all of you know how we get material properties. We do testing in a lab of coupons. So when we test, say, hundreds of samples, we will get some strength and some variation. So all the tested curves will not be the same. There will be some. So you have, what we have is, basically we have a band. So we have a lower bound and we have a upper bound for the modulus. Okay. And then similarly, we will have something for sigma y. So now, if we look at these distributions, there will be some distribution for modulus. Now, depending on what is the, confidence level up to which you want to design, 6 sigma, or for example, 6 sigma design means you are going 6 standard deviations, away. So that means you are not going to, your failure chance you're taking is extremely low, like 1 in million times. So that means your safety factor then will be decided based on that. So in this case, you decide, unless your problem statement gives something, you can decide the safety factor that you want to put on your material properties based on some general distribution data that you might get for your properties. Typically you can take, for material properties, since you are just doing a demonstration, you can take it like 1.5 or something and put it, or and then similarly for loads, again the same thing. Loads also you can never estimate 100%, so there will be some variation in the loads. So if you measure, say, aerodynamic loads once, twice, thrice, you will get a slight variation. Now that will be again a lower bound and upper bound. So depending on where you put your loads, are you going to put your loads here, depending on that, your safety factor basically will be a factor which you multiply. So in case of loads, you multiply with the safety factor. In case of material properties, you divide by the safety factor. Okay, so based on that, then you can, after doing this, you can do your design. Then in the design, you check for deflection of the structure under the loads, identify the max deflection, and make sure that you also keep track of which is the load case for which it turned out to be maximum. Then check for stresses and identify the maximum stress region and the load case. So basically there could be an iteration between these two, because we would have started off with some geometry, tried different geometries till we reach a situation where deflection is within the allowable limit. And if the deflection is within allowable limit, then we go for checking for stresses. And then we say, okay, if stress is also within the allowable limit, then great. If not, then I have to again go back and change the geometry so that I get my stress also within the limits. And once that is done, the final structural check that has to be done is for buckling, because everything could be correct from a stress and deflection point of view, but there could be thin members or thin plates or anything in a structure which can actually undergo buckling under the applied load. So buckling analysis also has to be done, a linear buckling analysis, and then you can identify the load factor. Make sure that your load factor is more than 1, typically 1.25, like that. But in this case also, one could, if you want to apply, one sec. If you want to apply safety factor, then modulus could be degraded here. So again, that's a choice you can decide based on your material properties. You can degrade it by say 10% or 15% and do the buckling analysis and make sure that the load factor is more than 1. So this way you can, basically these are the 3 key things: deflection, stress, and buckling. Other things are, will be covered pretty much under this. So that is the really short and fast wrap on how to go about a general design approach. The other thing, if you have some specific things like you're cutting some composite material somewhere in the middle or making a big cutout for something, then it is better if you do some quick analysis of that detailed geometry under the applied loads. But again, since this will be like a more of a preliminary design document, may not be required, but this is something that you should keep in mind, that if you're doing some really sharp, like some specific, something really in the main structural frame, if you're cutting this or putting some attachment, then it is better to do a quick check on that to make sure that, it is within it's not creating additional problems in the structure. So I think with that, I'll stop. Maybe there are 10-15 minutes per question answer, if there are any questions.
Yeah, great. So let us open up the webinar for any queries now. So there are 27 people in this meeting, and then there are, I hope, a few in the YouTube channel, which is also being webcast live. So if you can stop sharing the screen, then we can see the people.
Okay.
Okay, so friends, the floor is open. Any query that you have related to the structural design of the problem that you are facing, this is the time for you to ask. If you cannot speak, you can send your message via chat window. And we will request Pranav to monitor the YouTube stream if there are any queries from the YouTube side. The floor is open. So, Chandrasekhar, there is one query in the chat window.
So the question is, do you recommend going for idealization based analysis or FEM based ones? See, if it depends. Say if it's a simple quadcopter, technically you can just idealize it as, you know, a cantilever beam, and wherever the, you know, the rotors are located, that becomes the load point, and you can create a moment diagram and you can do the analysis. If you are comfortable doing that, I think that should be good enough for this first cut design analysis. There is no need to go and do a full FE model and all that.
Yeah, if I can just add, you may not have the wherewithal as well as the bandwidth right now to do a complete FEM analysis, because that may require too many elements and the typical packages that students are prescribing in the colleges. Of course, we have made it very clear right from beginning that we will not encourage any, any, shall I say, unlicensed packages. We have requested the principals to ensure that students only use licensed software. It is unlikely that a licensed software available to the college will be so large in size that it can handle the entire FEM. But if you want to do, you're okay. But as Chandrasekhar mentioned, it's a overkill.
Yeah,
it's probably.
But I mean, it's like this. If first of all, if you are all undergrads, maybe you may not be proficient in FEM. But if you are, you can try it out. I will not say no, but if you can do a good strength of material basic analysis is good enough actually for most of these things. If you think about it, you can idealize the structure and do the loads, put the loads in the right location, make bending moment diagram, shear force diagrams, and you should be able to get most of the analysis right, and that should be good enough.
Agreed. I agree with you. Okay. Anyone else? Thank you, Shobit, for this question.
But when you are doing the idealization, just one thing, make sure that don't look at your problem as a 2D problem or something, because you could have differential loading in the, in the all the axes. So because of which there can be a twisting moment combination with a bending, like in plane bending moment. So all these things you make sure that you are considering all. So the solution, either you can solve it in a decoupled manner and solve it and then superpose, or you want to look at it in a combined manner, you will have to solve a 3D beam problem. Even that, Timoshenko or any of the books have solutions for that also. But just make sure that you're considering all the loads. Just because you're idealizing the geometry problem doesn't mean you should idealize the loads. The loads have to be accounted for. All the loads have to be accounted for. So how to do sizing of different structural elements like stringer, longer on? We should go iterative analysis, or we have any method for that? See, I think if you look up aircraft structures books, there are guidelines on these things. But iterative, it's not like you'll have to do a lot of iteration, first of all, because you could, try one or two iterations. As see, if you are going by analytical approach, you could program everything all of this into an Excel spreadsheet, and you can iterate it actually, or MATLAB or whatever. You can, put in the formulas, analytical formulas, and just do the calculations and make sure that you are all, you just put a loop and, iterate it couple of whatever number of times required before you get to the right geometry. But the other thing actually, it's a good question. See, when you do stringers, longerons and all these things, you will be using some profiles. Now, these profiles are not available in every geometry and size that you want. So make sure to first check your vendors and suppliers on what kind of section geometries are available. For example, if you take a C section, there are only some finite sizes that will be available. In the design iteration, you can go in a continuous manner, but you suppose arrive with some geometry where the web thickness is 4 mm. But maybe the profile that is available in the market may not have a 4 mm web with a flange width of, say, 100 mm, may not be available. They might have only standard sizes which are going like 80 by 2 or 100 by 6 or something like that. So make sure that when you are doing these design calculations, to look up your supplier database, or talk to your supplier, or talk to whoever from wherever you're going to source these materials and these sections and all that, that what geometries and what dimensions they're available, and only use those in your design calculation. Because there's no point designing and coming up with a geometry which is not available readily. It will just make your life difficult, and also you will find it difficult to source them. Okay, cost also will increase. Could you? Oh, okay. Okay, it went down twice.
There's something regarding some good books.
Good books for reference for structural design analysis. I mean, this aircraft structures by Maxon, I think covers a lot of these things. Although, see, as I said, design in aircraft structures, like, I don't know what you mean, but aircraft structural design analysis, Maxon will do. Maxon has a good section on aircraft structures in the back. It doesn't necessarily do design as such, but it does have a lot of information on different sections and all that. See, the thing is that some of this will go into mechanical. Actually, if you do mechanical engineering, or some of these have these design handbooks, that kind of thing, maybe you should refer. But I don't know offhand. I don't remember anything other. I think you can start with Maxon as a basis, and then from there you can look up. But as I said, what you are learning in strength of materials is good enough to do these things actually at this point for what you're doing.
So Chandrasekhar, there is this book by Bruhan, Aircraft Structures.
Correct, Bruhan.
That it's an old one, but I think it has got very systematically all the calculations relevant for aircraft.
That's also a good book actually, and that's, I think, available online also. Yes,
it's also available online. Correct, it's available free online. It's a very big book, more than 450 pages.
BRUEHN, I think, no?
BRUHN actually.
BRUHN, yes.
BRUHN.
Yeah.
Yeah, aircraft structures. Analysis and design of flight vehicle structures. It is 996 pages.
Yeah.
I will just share the link with people on everyone. Flight vehicle structures. I remember we used to refer to this book during our structural design or structural analysis classes. So very elaborate.
I have seen this. For landing gear design, I have seen this part.
Yeah.
Any other?
Okay, any other point? We have another 5 minutes remaining because we have kept this webinar for 1 hour exactly, and we have only 5 minutes remaining. To be precise, only 4 minutes. So it's up to you. Dr. Ramchandra, you would like to add something?
I'm not adding anything, but then it's a well-structured presentation for the basics for the students. But I had a curious question, since Professor Aramali mentioned about lightning loads, and I know it has got a lot of effect on EMI, EMC, and that's an important conceptual design factor for the medical drone ambulance that they're designing. So that is a good input. But then I was curious, just a curiosity, nothing to do with the conceptual design. Are there any lightning loads, mechanic loads, likely to come onto a flying vehicle, Professor? So
No. That's what I said. That's why I said it's technically not a load as such, but the structure has to be protected so that damage doesn't happen. Because if damage happens, then the regular loads will make the thing crash.
Right.
So it is in a way indirectly going to affect. So usually some type of lightning conductor system has to be incorporated.
Right.
So that the lightning itself, although people do say there is a air pressure load, like the acoustic, some load is there, but I think that is not significant compared to the normal mechanical loads already the structure has been designed for. So that is not a big issue, but the bigger challenge is to make sure that there is no damage that is caused because of the lightning event, which can then, under the action of mechanical loads become a danger point.
Very well. Since Professor Pant asked me if I could add anything, I was wondering, because it's a medical drone, there's an ambulance.
Correct.
It's important to have low impact loads, and therefore you need to perhaps design the vehicle for impact situation. Maybe there is an uncontrolled thud coming from a
so
side.
That is true. There are a lot of those kind of situations that have to be accounted for. Impact loads, one has to decide actually what is the height up to which you are going to allow.
Right.
Because beyond a certain height, it may be impossible. But like, just before landing, if there is a propeller, one propeller goes down or, doesn't work, whatever. Those kind of, what is the max acceleration or deceleration you are going to allow in that? That I think has to be done. Yes. It will go into landing gear design technically, but or whatever the skids or something, if they are making, that will have to take that load.
Right. Yeah. Since there's a shortage of time, thank you, Professor. I hand over to Dr. Pant.
Great. Very nice. So students and other participants of this webinar, we have just 1 more minute to go. So Chandrasekhar, is it possible for you to just share your email address, because some students may would like to contact you for some suggestions after the webinar?
Not a problem.
If you can just share your email address in the chat window.
Yeah.
Of course, they cannot expect an instant reply. They have to wait till you get the time to respond. And some queries may be difficult to respond also.
Fine. I mean, if it is required, I can also, I can also meet with them. They can set up a meeting and, online meeting, and we can discuss. That is not an issue. But do email me if there are any questions.
Aryaman has a question. Any must-read books for first-year aeronautical students?
I think first is read all your books for the syllabus, whatever syllabus is there. I think they are the must-read books. Beyond that, I think it's okay. Just go gradually. Syllabus has been designed in such a manner that you will pick up everything. If you follow the syllabus, I think you will learn everything. So, but you can always read. I don't like to recommend reading more technical books. I would rather that you read some aerospace related books, but maybe historical books or history of, how some airplanes are, or, like just learn about the general context in which aerospace has developed. That might give you a much more motivation and interest in this whole subject. And make sure that you are reading all your syllabus books diligently.
Okay. I think that brings us to the end of our sessions. We have already crossed it by a minute. So, okay, Lakshmi Sheshadri Upala has, can we please have a webinar on autonomous system design? Yes, we will try. Thank you so much. You can send a mail to us on the NACDeC email address or even on the WhatsApp group, and then we will try to arrange a webinar on autonomous system design. So with that, I would like to bring an end to today's webinar and thank my colleague Chandrasekhar for this very nice webinar. As I mentioned, this webinar is now also available on the YouTube for keeps. It is already uploaded. So you can request your friends who could not join today to watch the webinar at leisure. Thanks a lot. A very good evening to everyone. And I'm going to now end the meeting.
Thank you. Thank you, Professor.
Thank you,
Thank you,
so much.
Dr. Ramchandra.